Here we're going to take a look at HIV infections, and it has to do with children that acquire it from their birth parent. So perinatally, they're obtaining it in utero, basically. It says an incidence of perinatally acquired HIV infection less than 1 per 100,000 live births is one of the Centers for Control and Prevention's, or CDC's, goals. Use the data below to determine if the goal can be achieved. We're going to go ahead and plot the data, and this time it looks like it graphed it right for us. Problem 3 says interpret the point 1978 and 2.1. What that means is in 1978, there were 2.1 out of 100,000 births with HIV infection. Any questions on that interpretation? Let's take a look at number 14. It says describe the behavior of the graph. Good. Okay, so peaks in 1990. So in 1990, there were about 41 children out of every 100,000 born with HIV. Okay. Now, what trend have you seen since 1990? Yeah, we've had a decrease since then. Why do you suppose we've had a decrease since 1990? Medicine, that's right. Knowledge of how it's transmitted. I'm going to go ahead and load this data into Excel. Give me a moment to do that. All right, so based on our scatter plot, the equation that we had, hopefully you've written down, is y equals negative 0.1x squared plus 419x minus 417,697. Crazy numbers. It says, using the equation, what is the estimated number of infants infected with HIV in, right now, 2018? So we're going to substitute 2018 into this equation. Definitely grab your calculators. Okay, so we all came up with some large number, and I got y equaled 20,612.6. The reason why that's happening, if we look at our graph, is we can see that the parabola doesn't fit our values very well at all. And so when we have an equation that doesn't seem to fit our values very well, using the equation will just give you kind of ridiculous answers, which is too bad. But that's what happens. Let's take a look back at the document and see what question 17 is. The 17 says, will the CDC meet their goal of less than 1 infected infant per 100,000 live births? So I'm going to go ahead and just look at our graph. We'll just look at the graph itself. When we look at the points without the trend line, let's see if I can take off the trend line. That's what I'm wondering too. Right. Okay, so if we take a look at the points without the trend line, does it look like the CDC will ever have an opportunity to only have one infected child per 100,000? You say yes, and Tara said no. Why do you say yes? You think that it will eventually get down? It's a valid argument. Tara, what's your argument?
I'm not thinking that.
And so when you're thinking that, what evidence or thoughts do you have?
Just medicine.
Okay. Yeah. So it is going to be curious. There is kind of what we call a plateau. There is some sort of plateauing going on in here where they're going to hit some sort of barrier that we don't know. Is it going to be 1? Is it going to be 2? Is it going to be 3 where we're already at? Are we going to be able to drop down? The next question would be, is it ever going to be 0? And the answer is no, because we're always going to have the HIV virus around. Symptomatic, maybe that'll be at 0. But this will somewhere be between 1, 2, or 3, and the goal is to eventually get there. How long it's going to take to get there, that's the big question. You can put whatever answer you feel comfortable with. There's no right answer. The next problem has the title, Traditional Application Problems Connected to Notation. So this will be more of what you'll see in Math Excel. Okay. Number 18 says, the height h of a fireball launched from a Roman candle with an initial velocity of 128 feet per second is given by the equation h equals negative 16 t squared plus 128 t, where t is the time in seconds after the launch. Question A, what is the maximum height of the fireball or the vertex? And that's an appropriate question because if we were to look at the equation has an a value there that's negative 16. So we know that our graph is going to open down, which means our vertex is going to be maximizing it. So we're going to calculate our vertex with our skills that we've used before and you were doing in your homework the last couple days. So that vertex is found by taking x equals negative b over 2a, and we take the b value, which is 128. So we have a negative from the formula and 128 from our equation. Then we're going to divide by 2 multiplied with the negative 16. On a calculator, a negative 128 divided by that negative 32 will end up being a positive 4. And I didn't expect it to be such a nice number. Now I want to find the y value. If I plug the 4 into the equation, I would have negative 16 times 4 squared plus 128 multiplied with 4. Utilizing technology, that ends up being 256. So we know our vertex is the ordered pair 4, 256. Now, as I was doing this problem, I utilized the values x and y for variables, just because that's what you're familiar with. But it's not completely technically correct for me to use x and y, because instead of x, we're using t. I'm going to go ahead and go on this left-hand side of the first line that I wrote, and I'm going to change that to t instead of x, because this equation was using a t. Okay. And instead of y, what variable should I put there? H. Very good. question A had said, what is the maximum height of the fireball? So if we look at the ordered pair, we know that the 4 is T, and we know that the 256 is H. So how would we interpret and answer that question? Yep, 256. Good. And that's going to be in feet. Question B, when is the fireball at its maximum height? When is it? Well, the vertex will tell us that. When was it? Good, at 4 seconds. Question C, when will the fireball return to the ground? And that's like an x-intercept. How do we find x-intercepts? A table of values. Table of values. So we know that this Roman candle was on the ground, and it went up, and then it needs to come back down because gravity is going to affect it. If we pause and think about this, we actually can arrive at our answer. When did it hit the maximum height? At 4 seconds. And we know parabolas are symmetric. So if from the time it was thrown to the time it was at its maximum height was 4 seconds, how much more time will it take to fall down? 4 more seconds. So overall, it'll take 8 seconds to go from being launched to returning to the ground. Now, if you forget that perspective when you're working on your homework, feel free to build yourself a table of values. And I'm going to build it horizontally and do it rather quickly just so you can see it. We know that our vertex was at 256. And we know that was the maximum height of the ball, which means that I know we need more time to come down. So I'm going to add time 5 seconds, 6, 7, 8, and I'll put a number 9 in there just because if I hadn't gone through the logic of the 4 plus 4 equaling 8 seconds, I wouldn't know when to stop my table. Then I would one at a time substitute the 5, 6, 7, 8, and 9 into the original equation. So I would first go negative 16 multiplied with 5 squared plus 128 multiplied with 5. Utilizing the calculator to do all these calculations, at 5 seconds, the height is 240. At 6 seconds, it's 192. 7 seconds is 112. At 8 seconds, it's 0. And this equation would tell you at 9 seconds, it is down in the ground to negative 144 feet, which wouldn't make sense. You guys have seen what happens when you shoot something up and shoot it back down. Sure, when it comes back down, it might bounce on the ground or it might make a small hole, but it's not going to go a negative 144 feet into the ground. Okay, so you have to be realistic about that. Any questions about number 18?